Today, I'd like to present a result that is joined with Dan Cristofaro-Gardiner and Rohil Prasad. So let me first give the statement of our main result. The setup of our theorem is that we take a closed oriented surface sigma that is equipped with an area form omega sigma. And let's suppose that we fix an area preserving diffeomorphism and call it on sigma and call the map phi. Then the main result that I would like to present today is the following statement. For every open set U on sigma, and for every given open neighborhood V of the map phi in the C infinity topology, we claim that there's always an area preserving map phi prime in that open neighborhood such that phi prime has a periodic point in U. So the statement is relatively elementary. Just remark on the necessity of the assumption on that phi has to be area preserving. Well, in fact, if we consider the following example where we take the surface sigma to be the one-point compactification of the set of complex numbers, topologically this would be an S2, then we can consider a map from S2 to S2 given by rescaling the points on C, and we assume that the rescaling factor lambda has norm not equal to 0 or 1. In this case, of course, phi is a diffeomorphism on S2. But on the other hand, it is easy to see that if we take an open set U such that the closure of U is disjoint from 0 or infinity, then when we apply the map phi sufficiently many times on U, we're going to get a set that is disjoint from the closure. In this case, it is easy to see that we can find a sufficiently small open neighborhood of phi such that there can be no periodic points in U for every phi prime in V. So it turns out that there are counterexamples to the statements if we don't require the map phi to be area preserving. An interesting corollary of our main result is that we can have the following statement. It turns out that for a generic area preserving map on a closed and oriented surface sigma, we can conclude that the set of periodic orbits or the set of periodic points of that map has to be dense. And the proof follows from our main theorem and a now standard Baire category argument. So let me give a sketch of the proof of the corollary, assuming the main result. We first fix a Riemannian metric on sigma that is compact. We take a countable dense subset of sigma, and we take a positive sequence Rn such that it converges to 0. Let's define Un to be the open ball centered at Pn with radius Rn. Then we can define a set V to be the set of smooth area preserving maps such that there's a non-degenerate periodic point in each UN. Since we're assuming that the periodic point has to be non-degenerate, if we have a periodic point in UN, then after small perturbation, we still have a periodic point in the same open set. So that implies the set V is a G delta set. But on the other hand, our previous theorem that V is dense is actually not immediate from the theorem, but it follows by a short argument. So in conclusion, we see that V is a set of Baire's second category in the set of C infinity area preserving maps, and therefore for a generic point for a generic map in the space, we know that dense. The kind of results similar to our main theorem are usually referred to as the closing lemma. And in fact, the study of closing lemmas is, well, the study of different versions of closing lemmas is an interesting topic in dynamic system and has attracted a lot of attention recently. It can be traced back to what the first closing lemma can probably be traced back to a result of Puyin, where he proved that for a C1 map on a closed manifold in arbitrary dimension, and if we look at the neighborhood of a so-called non-varying point, then after a C1 perturbation, there's always a closed orbit in that neighborhood. The extension of Pugh's closing lemma to higher regularity is the content of the 10th problem on Smale's problem list. And the version for area-preserving maps on closed surfaces was a question asked by Frank and Le in a paper in 2003. Since then, many people have studied this question, and in particular, in 2016, Ahsoka and Irie proved a version of the closing lemma for Hamiltonian diffeomorphisms on surfaces. More recently, Chu and Xia proved the smooth closing lemma for diffeomorphisms, for area-preserving diffeomorphisms on a torus that is isotopic to the identity. More recently, while we were preparing our paper, used a different method to prove that all diffeomorphisms satisfying a so-called U-cycle condition of Floer homology would satisfy the closing lemma. And later, it turns out that this condition always holds after we take a small perturbation on area-preserving maps. So that is actually an indicator for the closing lemma. So that was the statement of the main result and some brief history. Before I move on to discuss the ideas in the proof of the result, let me take a pause here and see if we have any questions or comments on the main result. Okay, so if we don't have any questions, let me move on and discuss some of the main ingredients that goes into the proof. The proof of the closing lemma actually uses a machinery called Floer homology. Floer homology has now become a widely used tool in the study of low-dimensional topology. And we're going to use a particular version of Floer homology, which is called periodic Floer homology, that turns out to be very convenient when we need to study the dynamical systems on surfaces. So let me introduce some notations here. An area from on a closed surface, which is called sigma. And now let's define the mapping torus of phi to be given by first taking the cylinder over sigma and then gluing the two ends together using the map phi. Then the manifold M phi is a closed three manifold. And if we take the image of the vector field defined by the t coordinate, where t is the coordinate on the interval for this cylinder, then R is a vector field over M phi. And we can also define a two-form omega phi, which is the pullback of omega sigma to the cylinder, because we're assuming that the map phi is area preserving. So a closed two-form on the three manifold M phi. And by local computation, it is easy to verify that actually the vector R is in the kernel of the two-form omega phi, or more precisely, if we contract the vector R with the two-form omega phi, we get a zero form. There's also a projection from M phi to S1 because it's a fiber bundle over S1 with fibers diffeomorphic to sigma. Using this projection, we can define a concept of degree for elements in the first homology of M phi. Basically, if we have an element in H1 of M phi, we can consider its image in S1 and use that image to define the degree of this element. So this is the setup of the definition of periodic Floer homology. And now to write down definition of a homology, we need to assume that all the closed or non-degenerate by some standard arguments, we can show that this is a generic condition. So after generic perturbation, we can make sure that all the closed orbits of R are indeed non-degenerate. And also we fix an element gamma with positive degree. There's a technical condition on the homology here, which is usually referred to monotonicity condition. And in our case, we have to assume that this particular homology class, cohomology class, is proportional to the cohomology represented by omega phi. The monotonicity condition is a technical condition that is usually present in the definition of Floer homology to ensure that to avoid some technicality involving non-compactness of certain moduli spaces. And now we define the concept of orbit set. By definition, an orbit set is a union of embedded closed orbits of R, and here we're actually counting the embedded orbits with multiplicity, such that first of all, the fundamental class has to be equal to gamma. And second, there's also a technical restriction on the so-called hyperbolic orbits that we're not going to get into details here, but we can just think about orbit set as a union of embedded closed orbits with fundamental class equal to gamma, although more precisely, there are actually some other technical conditions we have to impose. With all these notation above, we can finally define the chain complex that defines the periodic Floer homology. Floer homology is the free abelian group generated by the orbit sets. And the differentials are given by the counting of J homomorphic curves with index 1 between those orbit sets. It turns out that one can prove that the square of the differential is 0 in this case, and therefore we can obtain a homology group. And that homology group is called the periodic Floer homology. By definition, it is easy to see that, well, for example, if we have a map that does not have any closed orbit at all, then there will be no orbit set, and as a consequence, the chain complex would be a 0 complex, and the periodic Floer homology would be 0. So already we see a simple relationship between the periodic Floer homology and periodic points of map phi, in the sense that if we knew that the periodic Floer homology is non-vanishing, then that automatically implies that there must be periodic points for the map. Well, it turns out that we have to further upgrade the theory a little bit and introduce a more convoluted concept called the twisted PFH. The twisted PFH is like a more refined version of the PFH in some sense. We keep track of more information. More precisely, we're going to fix an oriented closed one manifold theta with fundamental class gamma. And instead of taking the orbit sets to be the generators, we are going to take the pairs alpha and z to be the generators of the twisted PFH. In this case, alpha is an orbit set, and z by definition is a 2-chain in the 3-manifold M phi, such that the boundary of z and theta. Recall that because we're assuming that both alpha and theta have the same homology class in the 3-manifold, so whenever we choose an alpha, we can always find such a z. Also, 2 sets z1, z2 are constant if their difference is no homologous in the 3-manifold. And here we're using the bracket z to denote the equivalence classes represented by z. Morally speaking, this definition is just saying that we're not only keeping track of the orbit set, we also keep track of some 2-dimensional homology class whose boundary realizes this orbit set. We can define the differentials in pretty much the same way as in the previous definition. So by definition, the differentials from alpha z to, let's say, beta w is given by a counting of J homomorphic curves from alpha to beta. And in this case, we also require that the J homomorphic curve, or the homology class of to labels z and w. And more precisely, we require that the J homomorphic curves are homologous to the homology of w minus z. By definition, a priori, we see that the twisted PFH is actually, well, the definition of twisted PFH depends on the choice of a one manifold theta, but it can be easily seen that as a homology group or as a chain complex, the twisted PFH is independent of the choice of theta up to isomorphism. And this is because if we have two different choices that they want, then we can always take a two chain such that the boundary of V realizes the difference of theta 1, theta 2. And in this case, we can easily define isomorphism on the chain level from the twisted PFH defined by theta 1 to the twisted PFH defined by theta 2. So as homology groups or as chain complexes up to isomorphisms, the definition of twisted PFH is independent of the choice of the two chain of the one chain theta. The reason that twisted PFH is more convenient to use than the original PFH is because we can actually define a Z grading on twisted PFH. On contrary, it turns out that there's no Z grading on the regular PFH, exactly because of the fact that this homology class can, the fact that we can have different choices of Z for a fixed choice of orbit set alpha. To define the Z grading on twisted PFH, so well, here are some technicalities here, but let me just mark that. So basically, we just take some kind of Chern class in a rough sense that is defined on the surface Z, and because Chern class is defined using homology, so we can show that such a Z grading is well defined on twisted PFH. It's not, the Z grading cannot be reduced to PFH because we can actually show that there is possible to have different Z gradings for two different choices of generators with the same orbit set but different choices of Z. Another concept that we can define with respect to twisted PFH, and again, this would be impossible if we're looking at the original PFH, is that we can consider the following functional. So for a generator alpha Z, we define its we define a function C on alpha Z, which takes value, which is defined to be the integration of omega phi over the two chain Z. Again, because Z is defined up to homology or up to equivalence relation defined by being homologous to each other, we see that this integration is well defined on the equivalence class. So we indeed have a defined functional on the set of generators for the twisted PFH. And again, this functional does not exist, at least as a function to R for the original PFH, because we didn't have these two class or the two chains Z in the definition of the original PFH. And by definition, see that the integration of omega phi on C has to be non-negative. So for each fixed value of L, if we look at the set of generators such that if the value of the function of C is less than or equal to L, then these generators will induce a subcomplex of the chain complex of twisted PFH. This allows us to define the so-called spectral invariants for homology classes in twisted PFH. And by definition, if we take a sigma in twisted PFH, so here we're using a notation that keeps track of not only phi, gamma, theta, but also a choice of geomorphic structure, or a choice of almost complex structure. And in this case, we define C of sigma to be the infimum of L, such that sigma can be represented by a linear combination of generators, such that each of the generators has functional less than or equal to L for all I. We call C sigma the spectral invariant of the homology class sigma in twisted. If we recall the definition, we might notice that the map C actually depends on the choice of the reference cycle theta, cycle theta. In fact, if we choose a different theta, then although twisted PFH as a homology group is isomorphism between different theta, the values of the function of C is shifted by a constant that depends on the choice of theta. So in general, the spectral invariance of twisted PFH depends on theta, and it's shifted by a constant if we change the choice of theta. Now, an important property of the spectral invariance is that it turns out that we can have a kind of asymptotic formula for the, this is going to be the crucial component in the proof of the closing lemma. And by asymptotic formula, what I mean is that we want to take a sequence of positive integers that goes to positive infinity, and for each element in that sequence, we take a homology class gamma, such that first of all it's monotone, and second it has degree given by that value, and let's call that number d. So we're going to take a homology class gamma d with degree d, such that phi gamma d is monotone. Now for each d, we can choose a reference cycle with degree d. Then we want to consider the asymptotic behavior of the ratio of the spectral invariant and the value of d. And it turns out that this ratio will have a nice limit behavior when we take d to positive infinity, and this will help us prove the closing lemma for the original map phi. But as we mentioned before, there are some issues here. First of all, if we just look at this formula, we might notice that it's impossible to prove anything, well, to prove any asymptotic for this ratio, simply because the value of C is not well defined. As we remarked before, the value of C depends on the choice of theta d, and for each different choice of theta d, it's shifted by a constant. And now because we're actually choosing a different theta d for a different value of d, this pretty much implies that there's no way for us to prove any limiting behavior for this ratio, simply because we can arbitrarily change or shift the value of C by choosing different choices of theta d. So to remedy this, instead of considering this ratio itself, we're going to take two different classes and consider the difference of this ratio with respect to two different classes. And by taking the difference of the ratio on two homology classes, we can cancel the dependence on theta d, and therefore obtain something that is more reasonable to study. So so those are some heavy notations here, but let me spend some time to explain the notation. So we're going to take two different maps that are Hamiltonian isotopic to each other, and we're going to take the difference of spectral invariance on these two classes to cancel the dependence on theta. And so here are some notations. We take a Hamiltonian diffeomorphism on sigma and call that phi of h, where h Hamiltonian function, and let's call the map phi prime to be the composition of phi and phi h. Then, because phi and phi prime are also topic to each other, so there's actually a diffeomorphism between their mapping tool, and we call this diffeomorphism M capitalized H. In this case, for each reference cycle theta d, we can consider a corresponding reference cycle theta d on the new mapping tori defined by the image under the push forward of H. And similarly, we choose trivializations of the normal bundles so that they are compatible with respect to the diffeomorphism. And we also use the map MH to identify the set of admissible almost complex structures on, well, this should be R cross M phi to the admissible almost complex structures on R cross M phi prime. So, well, basically, to briefly summarize this, we just identify M fine with M fine prime using the diffeomorphism MH, and whenever we define the spectral invariants, we make sure that the auxiliary data that we choose are compatible with each other on the two sides. And now, if we introduce the notations as above, then it turns out that here is an asymptotic formula that we can state. Suppose we have a class in with respect to the original map phi, and suppose we have another class in the twisted homology of the different map phi and prime. Then, if we take the difference of the two spectral invariants of these two homology classes and divide it by d, and then if we add some correction terms, and those are basically terms that are subtracting the additional quantities that comes from MH, then it turns out that as d approaches positive infinity, this number approaches the integration of the Hamiltonian over the three manifold. Now, if you're familiar with a similar spectral invariance for embedded context homology, then you might notice that this actually has a more or less a similar structure as the asymptotic formula for the spectral invariance for embedded context homology. Although I'd like to remark that the asymptotic formula for periodic Floer homology seems to be a lot more complicated, in the sense that, first of all, we actually have to take two different classes and two different groups in order to cancel the dependence on theta d. There are also some other technical reasons where the analysis and the proof of the asymptotic formula here is actually, well, at least for us, a lot of things are quite difficult and different from the proof of the asymptotic formula from ECH. Okay, so the asymptotic formula is the main ingredient in the proof of a closing lemma. It was first conjectured by Hutchings a couple of years ago. And assuming the asymptotic formula, and also assuming that we do have non-vanishing twisted periodic Floer homology groups, using a relatively short argument. So here is a proof of the closing lemma if we assume the asymptotic formula that we just stated before, and also assume the non-vanishing of twisted PFH. First of all, by some algebraic topology, we can that there indeed does exist a sequence gamma d such that the degrees of the gamma d diverge to positive infinity, and such that every gamma d is monotone. And now, recall that the closing lemma states that whenever we take an open set U on sigma, and every open neighborhood V of phi in the C infinity topology for area preserving maps, we can always perturb the map phi within V such that there's some periodic points on U. So if we want to prove the closing lemma using argument of contradiction, then the assumption would be that we can find an open set U and an open neighborhood V such that no matter how we perturb the map phi inside V, there's always no periodic points in U. But if there's no periodic points in U, then that means if we only perturb the map phi inside U, then the set of periodic points will not change. So that means that the orbit set does not change. So the chain complex, or the generators for the chain complex will, so the generators for the chain complex of the twist PFH does not change. And it turns out that if we use a Hamiltonian H that is supported in U to perturb the map phi, then we can even show that the spectral invariant can only change continuously. But because the set of orbits, the set of generators doesn't change, the possible values for spectral invariance can only take values as the the values of the functional C under the applied to the orbit set, and if the orbit set doesn't change, that's a fixed and discrete set, that's a fixed and countable set in R. So the only way to have a changing number inside that set is that we must have constant functions. So in other words, if we use a sufficiently small h as a Hamiltonian function to perturb phi, then all the spectral invariants must remain the same. And then, well, actually there's going to be also a correction term to the statement I just gave before because of the fact that the diffeomorphism MH is non-trivial. But at the end of the day, what we have is that this number has to be identically zero under the perturbation because of the continuity of the spectral invariants. Now, if we recall the statement of the closing lemma, we see that this number is exactly the first part of the left-hand side on the asymptotic formula. So if we know that this number is identical to zero, then after choosing the classes suit, we can use the asymptotic formula to show that the right-hand side also has to be zero, which implies that all sufficiently small Hamiltonian functions supported on U has to integrate to zero, which is obviously absurd, which and hence gives us a contradiction. So in conclusion, that is how we can prove the closing lemma if we assume the asymptotic formula and assume the non-vanishing of the twisted periodic Floer homology. Okay, so do we have any questions so far or any comments about this sketch of the proof? Great. Okay, so now there are two more things that we have to explain. The first thing we need to explain is why is this group of twisted periodic Floer homology non-vanishing. In fact, if you look at the two groups are vanishing, then of course we're just looking at a vacuous statement. So we have to prove the non-vanishing of the periodic Floer homology, and also we're going to explain a little bit about how the asymptotic formula is proved. It turns out that to prove the non-vanishing of the periodic Floer homology, and also to prove the asymptotic formula, for both statements we have to resort to the Seiberg Witten Floer homology. So let me spend some time to introduce the notation of Seiberg Witten Floer homology. By definition, as well, in this, the Seiberg Witten Floer homology can actually not only be defined on any oriented Riemannian three-manifold. And by definition, a spin C structure on such an oriented Riemannian three-manifold is a rank 2 Hermitian vector bundle along with an injective bundle mapped from the cotangent bundle of M to the Lie algebra of SU2 over the rank 2 Hermitian bundle. And we further require that it satisfies the following property, that under a positively oriented local orthonormal coframe, the matrices of the mapping CL are given by these three Pauli matrices. The map CL is usually called the Clifford multiplication, and the bundle S is usually called the spinor bundle for the spin C structure. A section of the spinor bundle is also usually called a spinor. Of course, we can identify the tangent bundle with the cotangent bundle using the metric on M, and in this case, the Clifford multiplication can also be defined on the tangent bundle. So the reason that spin C structures are related to periodic Floer homology is because whenever we choose a gamma in the first homology of the mapping tori, we can assign a canonical spin C structure. I'm not going to get into the details of the definition of the canonical spin C structure, but let me just remark that in this case, the spinor bundle is given by this bundle, where V is the vertical tangent bundle of the mapping torus. The Clifford multiplication on DT is exactly given by this diagonal matrix with respect to the decomposition above. Oh, and of course, we can also introduce the concept of spin C connections. A unitary connection B on the Hermitian bundle S is called the spin C connection, and only if the Clifford multiplication is flat with respect to the connection. In other words, we have this Leibniz rule when we take when we apply the connection on the Clifford multiplication action on the spinor S. So the standard Seiberg Witten equation is given as follows. It's an equation for the pair B and phi. It's a connection on the bundle, and psi, in other words, B is a spin C connection, and psi is a spinor. And the equation more or less looks like this. There are probably some additional terms if we think of B as a connection of E gamma, but let's not get into that for now. The first equation states that the curvature of B has to be given by some term that is a combination of the Clifford multiplication and C. If we write down the quadratic term with respect to phi, with respect to C, and also we require that C is vanished by the Dirac operator defined by the connection B. So I'm not going to get into the details of these notations here, but let me just remark that so this is this system of equation is usually considered as the standard Seiberg Witten equation. In our case, we're actually going to consider a perturbed Seiberg Witten equation. This equation was actually first introduced by Lee-Taubes in his proof of the Weinstein conjecture for the context geometry, for the case of contact forms. And it was used in the paper of Lee-Taubes relating the periodic Floer homology and Seiberg Witten Floer homology. And the equation is like this. So if you look at the equation, this part is pretty much the standard Seiberg Witten equation, but we have some additional terms here where this first term, well, the important part is actually this negative IR dt, because we're going to take R to be a constant, and later we're going to take R to diverge to positive infinity. So this is actually a perturbation whose norm diverges to positive infinity. Well, this is actually a constant term. It's some perturbation, and this is a term to fix the homology class. And C and S, those are some abstract perturbations to achieve the transversality for the equation. Do we have a question here? Okay. So anyway, so this is some technical equation that we're going to use. And also there's some functionals that we're going to refer to later. So there's a Chern-Simons functional. It's some value that's defined for the pair D, B, C, where it has to be defined with respect to a fixed base configuration. So we already see that this is somewhat similar to the structure of the discussion of PFH we had before. If we fix some kind of base configuration, then we can define some kind of functional on the generators in a certain sense. And there's also the Chern-Simons Dirac functional, which is given by even more complicated formula. But anyway, the punchline for these definitions that we can, it turns out that B-C is a solution to the perturbed Seiberg Witten equation, if and only if it is a critical point to the Chern-Simons Dirac functional. And in fact, this allows us to define a Floer homology, the generators to be the solutions to Seiberg Witten equations, and up to gauge transformations. Well, there's some technicalities that it turns out that reducible solutions need to be counted differently, but let me not get into the details of that. And the differentials are given by counting gradient flows of the Chern-Simons Dirac functional with index 1. A major theorem of Lee-Taubes states that it turns out that the periodic Floer homology is isomorphic to the Seiberg Witten Floer cohomology with, okay, so there's some other notation here. It's called the Seiberg Witten Floer cohomology with balanced perturbation. So that's the theorem that relates the previously defined periodic Floer homology to the Seiberg Witten Floer homology that we just used using connections on spin C structures. However, recall that we're actually considering twisted periodic Floer homology instead of just the ordinary periodic Floer homology here. So we also need to upgrade the Seiberg Witten Floer homology to a twisted version. And in this case, to the twisted Seiberg Witten Floer homology would be solutions to Seiberg Witten equations up to gauge transformations, but in this case, we require that the gauge transformations are isotopic to the identity. So if two solutions are related to each other by gauge transformation that is not isotopic to the, not homotopic to the identity, then they're considered as two different generators for twisted Seiberg Witten Floer homology. Again, the reducible solutions need to be counted differently, but let me not get into that. Similarly, the gradient flows of the Chern-Simons functional with index 1 defines the differentials for twisted Seiberg Witten Floer homology. And then the verbatim same argument as the proof of Lee-Taubes would show that the twisted PFH is isomorphic to the twisted Seiberg Witten Floer homology with valence perturbation. So that allows us to relate twisted PFH to twisted Seiberg Witten Floer homology. In particular, if we want to prove the non-vanishing of the torus by this isomorphism, we just need to prove the non-vanishing of the twisted Seiberg Witten Floer homology. And that is what we're going to introduce now. So to prove the non-vanishing theorem for the twisted Seiberg Witten Floer homology, we first prove non-vanishing theorem for non-twisted version of Seiberg Witten Floer homology. And here's the statement of our result. In fact, this result actually works for an arbitrary closed manifold. It turns out that if we take an arbitrary closed oriented three manifold, and if we take a spin C structure whose first Chern class is non-torsion, then if we consider the bar version of the Seiberg Witten, it turns out that this homology is always non-vanishing. Let me give a sketch of the proof here. The proof actually depends on some machinery developed by Kronheimer and Mravka on monopole Floer homology. So if we take the Picard torus of Y, which is, by the way, defined by this formula, then it turns out that there's a spectral sequence whose second page is equal to some homology over T with respect to a local coefficient system. Version of the monopole Floer homology. A direct computation shows that the homology group on the torus for this particular local coefficient system is finitely generated. So that implies that our homology, our bar version of monopole Floer homology is also finitely generated. Since everything's finitely generated, we have these two equations from the universal coefficient system, the universal coefficient theorem. And in particular, that means coefficient bar is non-vanishing. And now to show that the Q coefficient version is non-vanishing, it turns out that Kronheimer and Mravka computed the E3 page of that particular spectral sequence explicitly, and they show that all higher differentials are vanishing after the E3 page. So a direct computation of the E3 page verify that in narrow pair case, the homology group is always non-vanishing. As a consequence, we can show that the twisted multiple for homology, and in this case, we're going to take R to be Z over 2 simply because the Z2 coefficients are easier to use for periodic Floer homology. And in this case, we can prove that the twisted version of the multiple Floer homology is non-vanishing. And this follows from some abstract homological algebra. And I'm just going to go quickly and skim through here. It turns out that the twisted homology, the twisted multiple Floer homology in the bar version can be considered as the regular Seiberg Witten Floer homology with a local system defined by a polynomial ring. The fibers of the local systems are, in this case, isomorphic to this ring. And now if we consider the ideal in R generated by these elements, then we can see that the chain complex for the ordinary cohomology is given by the chain complex for the twisted cohomology with a base change. Previously, we have proved that this homology group is not acyclic. So it turns out that by a formal argument from homological algebra, we can use this to conclude that this chain complex cannot be acyclic as well. So that proves that this group has to be non-vanishing. It turns out that Lee-Taubes actually proved that the periodic Floer homology is not always isomorphic to this group, but it turns out that when the degree D is sufficiently large, then the periodic Floer homology is isomorphic to this group. So that implies that when the degree D is homology is not vanishing. Okay, so that finishes our argument for the non-vanishing result. And finally, let me give some remarks on the proof of the asymptotic formula. And again, this is actually probably the most difficult part in the whole proof. So the proof itself is fairly technical. So I'm going to only give a sketch of the ideas for the proof and not get into the details of the arguments. The proof of the asymptotic formula actually follows from some analysis on PDE using Seiberg Witten equations. So first of all, for each element sigma in the twisted monopole Floer homology, we can have spectral invariant. And in this case, instead of using the value of the function of C over the generators, we use the values of the Chern-Simons Dirac functional. And because recall that the differentials are defined by flow lines of the Chern-Simons Dirac functional, so we have a similar filtration of chain complexes. So that allows us to define a similar spectral invariant using the Chern-Simons Dirac functional for monopole Floer homology. And it turns out that one can prove that the Seiberg Witten spectral invariant recovers the PFH spectral invariant as R goes to positive infinity. So that actually is related to the proof of the Lee-Taubes isomorphism. Somehow, if we compare the corresponding generators under the Lee-Taubes isomorphism, we'll see that the PFH spectral invariant covered by Seiberg Witten spectral invariance if we let R to go to positive infinity. So instead of proving a asymptotic formula for PFH, we can instead prove a asymptotic formula for on the other hand, if we take the value where R equals 2 pi absolute value of rho, and in this case, rho is actually the monotonicity constant that comes up in the monotonicity condition, then for this particular value of R, it turns out that all the relevant solutions are reducible, so everything can be relatively easily computed, and we can just write down the Seiberg Witten spectral invariant relatively easily when R equals this particular value. And finally, we need to apply certain estimates in PDE, and in this case, we're going to need to use a spectral flow estimate to bound the difference of the spectral invariant between this particular value of R, which we understand very well, and the case when R goes to positive infinity, which recovers the PFH spectral invariant. So it turns out that if we work out all the analysis, let's see that they will imply the asymptotic formula for the periodic Floer homology spectral invariance. Okay, so I think that's all that I have for the talk. So I'm going to end here, and thank you very much for your attention. I'll stop here and see if you have any questions.
I have a quick question. What is the Lee-Taubes isomorphism?
Okay. Sorry. Lee-Taubes. I think it's in here. Yeah, it's in here.
Oh,
well, this is actually kind of a not so precise statement. Well, we should really say that this is there are actually 3 versions of Seiberg Witten Floer homology, and PFH is actually isomorphic to a particular version of the homology. I think it's actually I think it's the Czech version of the cohomology actually.
This might be a very naive question, but what is a balanced perturbation?
Oh, thanks. That's a great question. Actually, I didn't explain that. So for Seiberg Witten Floer homology, we can actually perturb the Chern-Simons functional, and we can actually perturb it in a way that is sometimes called a non-exact perturbation, in the sense that, okay, so let's look at the definition of the Chern-Simons Dirac functional. So this is the Chern-Simons Dirac functional, and let's see. Okay, so this is the Chern-Simons functional here, but okay, that's defined with respect to gamma. In general, for general 3 manifold, we can also write down formula for the Chern-Simons functional. And in this case, if we take a gauge transformation, then the Chern-Simons functional changes with respect to the gauge transformation. And there's a homological formula for that. It turns out that we can perturb the Seiberg Witten equation to obtain like different Floer homologies. And there are 2 different ways to perturb it. We can perturb it in a way so that the change of the value of the Chern-Simons functional or the Chern-Simons Dirac functional under gauge transformations, this form for some of the perturbations, this formula remains the same, in the sense that if we apply a gauge transformation, it still changes by the same amount. But if we take some more complicated perturbations, we can make it so that if we apply a gauge transformation, then actually the value of the Chern-Simons Dirac function will change by a different amount. And this is called a non-exact perturbation. So we can actually choose a perturbation so that the Chern-Simons Dirac function just does not change under gauge transformation. And that is called a balanced perturbation. So balanced perturbation is an example of a non-exact perturbation, where if you choose the homology classes of the certain terms correctly, then it will cancel the previous gauge, like the change of values under gauge transformation, and eventually we get a gauge invariant Chern-Simons Dirac function.